Point 3, understanding rational inputs. We're going to start looking at what it means when you have to evaluate an exponential function, but the exponent is not a whole number anymore. It's a fraction or it's a decimal. So just to refresh our memory, rational numbers are basically everybody except for irrationals. So it's whole numbers, but it's also fractions, right? It's whole numbers, but it could be fractions, it could be decimals, and it could be negative values of all of these. So those are what our rational numbers are. So now we're going to start looking at what it means to have something like 5 to the 1/3 power. And how do you even evaluate that? Or 6 to the 1/2, or 8 to the 2.5. So definitely have a calculator handy, and we will go ahead and get started. So in 3.2, we kind of skipped around a little bit. We're looking at Florida in the 1800s. In 1840, the population of Florida was about 54,500. So in 1840, the population was this. Between 1840 and 1860, the population grew exponentially, and it increased about 60% each decade. So find the population of Florida in 1850 and 1860. So I like to make a table of values. So I'm going to come off to the side here. I'm actually going to make it into 3 parts. So we're going to make X your input values, and then Y your outputs, your population. Ooh. And then here I'm going to put X is years. And I'm going to put what each of the X input values is referring to. So your initial measurement happened in 1840. So for our X, we're going to put that at 0. And that population was 54,500. Now each decade, it's increasing by 60%. So we have to take 60% of that 54,500. So we got to times it by 60%, but then we got to add this number to the population because it's increasing. And that's what's going to get us at a decade later. So at 1850, or what we would call 1 for our input value, so 1 full decade later, I don't know why I can't say later, this would be our population. So let's take a minute and let's bring up a calculator. If you don't have a graphing calculator at home, you can do this with your cell phone calculator, or Desmos actually has a calculator for us that we could use too, but I'll just bring up a calculator real quick and see what we got. I'm going to clear this out. So we're going to do 54,500. We're going to times that by 0.6. That's 32,700, but we're going to add it to the original 54,500. So we got 87,200. So 87,200. Let's do it again. So another decade later, so in 1860, another decade later, we increased by another 60%. So we're going to multiply this by 0.6. Then we got to add it to that previous amount, and that previous amount was 87,200. So we're going to add that to 87,200. So now we're looking at a population of 139,520. 139,520. So number 1's done. In 1850, we can even make it a point, or 1850, we got a population of 87,200. And then 1860, we're going to do 139,520. The population is a function f of the number of decades d after 1840. So we got to write an equation. So I'm going to write my function f as a population of the decade. And my original population was 54,500. What do I multiply by to get each of these numbers? Now, if you're saying I multiplied by 0.6, you're actually incorrect because I multiplied by 0.6, but then I added it back to the original value. When we add it back to the original value, then instead of saying we multiply by 0.6, we actually multiplied it by 1.6. And if you're not sure how that came up with, remember you can always get your growth factor by taking one number in the table, so 87,200, and dividing it by its previous number, its previous consecutive number, and this will always result in your growth factor. So let's try that real quick. 87,200 divided by 54,500. 87,200 divided by 54,500. When I divide those, I get my growth factor of 1.6. So that is my actual growth factor. So each previous population, to get to the next decade, we're going to multiply it by 1 to get the full amount, and then the 0.6 to get the additional amount that it's increasing by. And then I'm going to put a little d up here in the exponent because I'm measuring it by decade. So in number 3, part A, it wants you to explain what does f of 0.5 mean in this situation? Well, let's go ahead and look at our table over here. If I go backwards in my table, and this is why I made a 3-column table to kind of understand what this stuff means. If I go backwards from 0, if I go to 0.5, I'm halfway between 1840 and 1850. So 0.5 means that this is the year 1845. That's what that 0.5 is referring to. Guess I didn't need to draw those. Now, let's go ahead and look at B. Graph your function using graphing technology and then estimate the value of 0.5. Well, I guess I don't really know the point of estimating if I can just plug it into my equation, but we'll just do what it asks us to do. So let's go over there and graph it into Desmos. Now remember, when you graph it into Desmos, you got to use y for your function. So 54,500. 1.6 is my growth factor, and you got to use x for your inputs. So let's head over to Desmos. Gonna start graphing. I like to type it with my keyboard, so I'm just gonna attach that real quick. Okay, so y equals 54,500. In parentheses, my growth factor of 1.6 to the x power. Obviously, I don't see anything because I'm starting all the way at 54,500. So I'm going to move. I don't really care about, I guess, before 0. So let's scale this out. I recommend you guys graph on your phones and then just use your fingers to scale in and out. Just seems to be easier. Remember, if you see the y-axis is turning blue because I'm scaling just that while the x is staying the same. I gotta get all the way up there. I gotta keep going. Learn this with my Algebra 1 kiddos. Don't put a comma in, please. Don't use commas in Desmos. All right, here we are. I'm starting to see the curve. They want you to estimate it at 0.5. So I'm estimating, this is 100,000, this is 50,000. So at 0.5, we are right here. So that's 75,000? Did I do that right? 50, 60, 70, 80, 90, 50, 60, counting by 10,000. 70, okay, you know what? Let's call it just under 70,000. So 68,000 maybe? So on our graph, we'll go ahead and say it's about estimated to be about, what did we say, 68,000? That can't be right. We're starting at 54,000. Oh yeah, that does. I'm sorry, that does make sense because that's just slightly bigger than. That's probably right there between 54 and 87. That does make sense. Okay, good. All right, let's use a calculator. I kind of always like to use a calculator if they give us an equation to find my exact answer. So y is equal to 54,500, 1.6 to the 0.5. And to do this, we are going to bring up the, I'm going to bring up the graphing calculator. And I will also show you that I think Desmos also does these exponents too. That's not my graphing calculator. Let's go down here. It's been a while since I brought this one up. It's taking a while. All right, here we are. So it was 54,500, parentheses 1.6 as my growth factor, raise, so the up button, and then we're going to put 0.5 in. Look at that! 68,937. 68,937. I almost said 70,000, right? So 68,937. 37.6, so we'll say 900. We'll just round that up to the nearest person. 38. Based on the model, what was the population of Florida in 1858? 1858. Well, let's think about this. 1858 is, so if I come over here, if 1850, get rid of that real quick. If 1850 is an input value of 1, right? And 1860 is an input value of 2, then 1858 is 8/10, right? 8 of the 10 years of your decades have gone by. 8/10 is the same as 0.8 as a decimal. So I'm going to write this as 1.8 as my input value. And I'm going to come over here and figure it out with my calculator. Get me that. 500. 1.6 raised to the input value of 1.8. And this is why this lesson is all about rational exponents, exponents that are not pretty whole numbers. The fun part about your graphing calculator, copy and paste. Bring it on up, hit enter, change this to be 1.8. 1.8. And there we have it. 127,000. We'll round up to the nearest person. So 127,003. So in this one, so this is y equals 127, or we'll just write it out in words. Population 127,003 in 1858 based on the model.